Over the last 30 years, I've had two wonderful international collaborations. One with Helmut Rauch and his group in Vienna, Austria, and the other with Tony Klein and his group in Melbourne, Australia. And you see us there. A picture was actually taken in Sydney, Australia at a conference, international conference for neutron scattering in 2005. Actually, we began as competitors when we were all chasing the same minus sign. And as you have known for a very long time, that if you take a neutron, which is spin 1/2 fermion, and let it precess in a magnetic field, through 360 degrees, the sign of the wave function changes. Now, this fact is deeply embedded in quantum mechanics, but it hadn't been directly observed experimentally until 1975. And it was observed for the first time nearly simultaneously and independently by our three groups. And I think Rauch's paper and my paper were published almost on the same day, but in different journals. In Rauch's case, well, in Klein's case, the experiment was done with wavefront division interference across the ferromagnetic domain boundary. In Rauch's case and in my case, we used the single crystal silicon interferometer invented by Ulrich Banza for X-rays about 10 years earlier. It was invented, by the way, in the United States, although, you know, Banza is a German and part's a Brit, and it was invented at Cornell University in 1964. And the story about how I got involved in it and how I found this all out about try to do neutrons is a very long story. Probably deserves some kind of a book of the type that Silverman writes. Better sellers than our neutron interferometry book, because it will have other things in it. Well, it turned out that Aharonov and Susskind had proposed looking for this famous minus sign by electron interferometry in about 1967. And about the same time, Herb Bernstein, who sits here in the front row, suggested looking for it by neutron interferometry. It turns out that an appropriate interferometer of either type did not exist at the time, 1967, except in the mind of Basel. So here is Basel. Basel is entering Stern-Gerlach experiment. Something really essential happens here. Exactly two guys come out, oppositely polarized, but not a whole bunch of little guys. So Basel anticipated our experiment. He even anticipated Herb Bernstein, because this cartoon appeared, I think, in one of the Melbourne papers before 1967, Herb. Okay. So here is a schematic diagram of a Banza-Hart silicon interferometer, and also a picture of one below with a famous ruler. That ruler, it should say National Institute of Standards and Technology, but the only ruler I had in my shop was the one, you know, I have a collection of those. It said National Bureau of Standards from some time earlier. The interferometer consists of three upright perfect crystal plates attached to a common base. It's called LLL interferometer because it has three Laue transmission geometry crystal plates. And here I have an aluminum model of one. And you can see how the beams, actually the model is the same size. I won't leave here so you can hear me and record this. Here's the model, okay? It shows where the beams come through. And if you like, you can come up later. We take this, where the beams come off, have your picture taken, and you can go home, Herb, and tell your wife that you had one of Sam Werner's neutron interferometers in your hands. Okay? And nobody would know. I mean, it's about the same weight. It looks like a silicon interferometer, but it's an aluminum model of that interferometer. So the way it works, and Helmut Rauch explained this a bit on Monday, and let me tell you again how, from my point of view, how it works. Suppose you have a nominally monoenergetic neutron beam, say de Broglie wavelength, 2 angstroms coming into that interferometer, and directed along at the right angle to have for Bragg reflection off the, say, the 220 Bragg reflection planes in silicon, typical planes that we use. The 2 outgoing beams from the first crystal plate are coherent with respect to each other and at the right angle to satisfy the Bragg condition in the middle crystal plate near points B and C. And 2 of the beams that leave the middle crystal plate go and mix and interfere in the 3rd crystal plate near point D, and the outgoing beams then have embedded in them the wave function of the neutron that went around on path 2 and on path 1, depending upon the relative phase. The outgoing neutron beams are counted in helium-3 detectors, that in our case, and these helium-3 detectors are proportional detectors, and they have essentially 100% detection efficiency. So there you are. Voila. You have here a matter wave interferometer operating on a macroscopic scale, typically 10 to 20 centimeters in length, operating over with neutron wavelengths that are adjustable, say from 1 angstrom to 4 angstrom. These are the kind of things we use. If I change the relative phase of the beam traversing, say, path 2 relative to path 1 by rotating that phase rotator up there, so as to increase the path length, say, on path 2 relative to path 1, then the intensity and the outgoing beams will oscillate. So the intensity in, say, the C2 beam will go, say, up and down, up and down, up and down. Well, the intensity in the C3 beam will go down and up, down and up, down and up, 180 degrees out of phase. So as to conserve neutrons, this device does not, silicon does not absorb any neutrons. Turns out that the X-ray interferometer is different. If you look at the interferograms on the X-ray interferometer, the intensities go up and down, up and down, up and down in phase. So this is one of the homework problems that you have later on. But the neutron interferometer, the intensity in the 2 beams are 180 degrees out of phase. So the neutrons are being swapped back and forth between these 2 detectors as the internal phase of that interferometer changes. And this is magic by any standards. So I just changed the orientation of that phase flag, which is typically a 2 millimeter thick plate of aluminum. Okay. So here are some nice interferograms that were taken at NIST, showing a contrast of 88%. And thank you very much, Helmut, for showing our data on Monday. This is NIST data. They have equivalent data, so we tend to show each other's data just as a courtesy. So you see that what I said is that the sum of the 2 intensities is constant as the phase is shifted, because this device has there's no absorption in the device. So we have to really account for all the neutrons that come in. They must go out. Okay, so here's my agenda. So it's, I want to talk about the Aharonov-Kasher effect, the scalar Aharonov-Bohm effect, and then in the end I give a quiz. It's fair enough. Okay, and so that you can expect. So the last 10 minutes that I'm allowed extra will be giving this quiz. But you don't have to process the answers just to give the quiz. Okay. All right. Okay, suppose that I thread a line charge of density lambda through this closed loop of a neutron interferometer of the 2 beams, and I draw it schematically here. And as envisioned by Aharonov and Kasher, is this famous paper, in 1984. If the line charge is along Z and the neutron is polarized along Z, the canonical momentum of the neutron has an additional part to MV, namely mu cross E over C. It's an additional part. So in this particular case, the electric field is radial from the line charge, and magnetic moment, say, is polarized up the direction axis of quantization. So mu cross E is a solenoidal vector field, just like the solenoidal vector field A in the usual Aharonov-Bohm effect, as Tanimura talked about yesterday, in very much the same way. One gets this canonical momentum, which I write here, P is mv 1 over c mu cross E, very easily from the Hamiltonian, which I write there on the left in green. P squared over 2m minus 1 over mc mu cross E dot P. And that's the spin-orbit coupling term. Okay? And it leads to many things. It leads to this so-called Schwinger scattering, Mott scattering, and so on. So this is what enters the Hamiltonian. To get the canonical momentum, it's very easy. If you believe that, then you just use Hamilton's equation. It's R dot is equal to dH dP, and you get that canonical momentum. It must be true. Must be true. Well, the Aharonov-Kasher paper says many things. One of the things that they say is caused a great deal of consternation and difficulty amongst the neutron community, probably about in the atom community too, but they don't keep up with these things yet. And so they'll do one of these experiments like this too, but sooner or later, and they'll have the same consternation that my neutron friends have. There's no force on the neutron. And what they mean by that is no generalized force. That means there's no acceleration. So the neutron, as it goes past this line charge, it does not accelerate. The velocity does not change. Okay? The velocity doesn't change. That's very hard to understand qualitatively, because you're coming into a region where a neutron's seeing this spin-orbit coupling, and you think that, well, there's a gradient of that, and there should be an acceleration, and it turns out not to be true. So, so pay attention, because the quiz will have something to do with this in the end. Okay, so if you take that canonical momentum, that P is equal to mv 1 over c mu cross E, and you must do to get the phase shift, and that is mu is the magnetic dipole moment of the neutron, and lambda line charge density. Okay? Now, the important part of many important parts to this slide, but a important part is that this effect is topological. That is, it doesn't matter where I put the line charge through the loop. It doesn't matter where I put it. I can put it near point A, point B, near the path 2 or path 1. It doesn't matter. If that's the case, if you believe that, then I just as well put 2 line charges in there, double the effect, or 3, or 1,000,000. Right? And then make the effect 1,000,000 times as big. Well, putting 1,000,000 in there is exactly the same as putting an electrode in there. Maybe, say, a charged rod in the inside of the interferometer. Okay? So we will make use of the topological aspect of the Aharonov-Kasher paper for an experiment. So this, if you believe this, it leads to an experiment which I will now tell you about. Okay? So here is the experiment. Here is the LLL interferometer. The 3 blades of the interferometer here are colored in blue. Neutron comes in, say, there is, what is it, 1.477 angstroms at some Bragg angle, and goes around and comes out into the detectors. The line charge, or in this case it's an electrode, in the middle of the interferometer, where it says plus 22.5 kilovolts, and the other electrode minus 22.5 electrodes. So what you're doing is the loop is around, in the interferometer, is around that line charge. It's around an electrode, a series of line charges. All right? Now you'll notice there's also a little magnet there. It's colored in green. Okay, so I need that because I'm going to do spin precession interference to set the phase, the spin-dependent phase with that little magnet.
What is
okay.
big D?
Big D is the gap thickness in that electrode system. You see, lines of electric field from that center electrode must end somewhere, and we choose to let them end on a negative electrode. You could do it whatever you like, according, but that's the simplest way to do it. And D is the gap of that. In our case, it's the D is 1.5 millimeters. Okay, and the length of the gap is a couple of centimeters, 2.5 centimeters. And so we have 45 kilovolts across a gap of 1.5 millimeters. That's a rather large electric field. And the electrodes are made of polished stainless steel. That's about, it's a vacuum container, so the neutrons come into this vacuum container through a quartz window. And that's about as good as you can do in vacuum. Okay, and okay, so this, if you use the idea, the formula on the last page for the AC phase shift, 4 pi lambda mu over h bar c, and use Gauss's law, convert the charge to an electric field and therefore the potential difference over a gap distance d, you can write down what the formula is for the result. Numerical formula is for the phase shifts, 1.52 milliradians. Okay, now that's a very small phase shift for anybody that does interferometry, even very high precision optical interferometry. This is a very small phase shift. So how to measure such a small phase shift? Well, first of all, you have to carry out a spin-dependent precession interferograms. So we want to do a spin precession interferograms and set at the point of maximum slope and then turn on the electric field and turn it off, turn it to zero. So this is sort of the concept of how you would do this experiment. So first, do a spin precession interferogram. That's what I do there with that little magnet. So I make the neutron go around. So I'm doing this 2 pi, 4 pi precession experiment over and over in this experiment. So then what you do is set to the point of maximum slope and then turn on the electric field positive and then negative and then positive then negative for a very long period of time. I don't tell you about that. So the time is that you turn the electric field on positively for 10 minutes, count in both detectors, negatively for 10 minutes, count for 10 minutes, turn it to zero, count for 10 minutes, 30 minutes. Repeat this 30-minute cycle 10,921 times over a period of 2 years. That's how you measure a very small phase shift. Okay, so here's spin precession interferograms. Okay, so here, let's say look on the C3 interferogram. Set at that green point, say where it says 3 pi over 2. That's the spin-dependent phase, 3 pi over 2, and where the slope is positive. Turn the electric field on. Okay, 45 kilovolts over 1.5 millimeters. The intensity goes up a little bit. The blue point. Okay, actually it's only 1 part in 1,000, so it's really small. Turn it negative and goes down. Turn the electric field negative, goes to the red point, and then turn it to zero. And then you do that. So it's a 30-minute cycle. You do that 10,921 times over a period of 2 years. Okay, so so if you know the slope of that spin-dependent interferogram, and I know the difference counts from the blue point to the red point, okay, then I can convert that difference count to the abscissa, okay? How much the phase has moved on the abscissa. That's the Aharonov-Bohm phase shift. That's what I'm after. So I make a precision measurement of the difference counts and then convert it to a phase shift. That's what we're after. We're after this 1.51 milliradians, okay? Now, this experiment was done with unpolarized neutrons. How do you see a polarization-dependent effect with unpolarized neutrons? And it's shown here, okay? I've had Mike Horn as my supporter in these kinds of things, and he's explained it to many people over the years. And you know, because he takes care of the theorists, and you haven't taken as good care of the theorists as I've taken with the experimentalists. But some of them still don't get this point. Okay. So if you have spin-up neutrons, right, the interferogram looks of the form A plus B cosine alpha plus beta. For spin-down neutrons, it's A plus B cosine alpha minus beta. So if you have unpolarized neutrons, the interferogram should be of the form A plus B cosine alpha times cosine beta. Okay? So what I must do if I use unpolarized neutrons, first I must set that spin-independent phase, which I call alpha there, to 0 or pi or something, so as to maximize the amplitude of the oscillations in the spin-dependent interferogram. So I have to do that. Now, clearly I could do that by taking the phase rotator, the thing I showed in the first slide, piece of aluminum, and rotating it. But it turns out that we had a lot of stuff in this little interferometer, you know. So this is the size of it. This had a lot of stuff. High voltage vacuum container, a little magnet, all the time. There just wasn't room in here to put another phase flag and hook to some stepping motor. It was not room. So what we did is we set the spin independent phase alpha, to make that cosine alpha, say 1, by gravity, by gravitationally induced quantum interference. That's using the so-called COW effect. That is, you take this, this interferometer, and when it's horizontal, the two beam paths see the same gravitational field from the Earth. You turn it up like this, and you change the gravitational potential. One beam path a little bit higher above the surface of the Earth than the other. It's called COW. Okay, so we use this effect. So you see, in order to do this experiment, to see the AC effect, which is dependent upon the electric field, we actually have to use the magnetic field, spin precession, and gravitational field in order to set these phases. Okay, this is really the case. Okay, no problem now. We can do polarization-dependent experiments with unpolarized neutrons. Everybody believes this. Okay. Now, I would like to make one point about it, however. If you would try to do this experiment with polarized neutrons, and we originally thought we must do it with polarized neutrons because AC phase shift depends upon the polarization of the neutron, depends upon sigma plus or minus 1. But we'd already done spin precession, so we knew this trick. But if you tried it with polarized neutrons, you would certainly fail for all kinds of reasons. One is you're down in intensity by at least a factor of 5, maybe 10 for going to polarized neutrons. That's one. The other thing is the interferogram then is of the form A plus B, cosine alpha plus beta. And all phase drifts caused by temperature variations, vibrations, all those things will kill you. Will just wipe you out. But here, those phase drifts appear as an amplitude. You see cosine alpha. And that doesn't matter. It's because you're at the top of a cosine curve. It doesn't matter if it drifts around a little. And we readjust those things. We had readjusted those things every day. The experiment, as I say, went on for 2 years. But we readjust those things. That changed, but the spin-independent phase, beta, is rock solid. That depends upon the magnetic fields that you have around. And the magnetic fields in this experiment were produced by an adjustable permanent magnet little reluctance circuit. It generated no heat, and we could adjust it. Okay, this goes back in time. That's what we did originally in our spin precession experiments. Okay, so there we are. So here's a whole series of interferograms. Ones on the left are spin precession interferograms for various tilt angles of the interferometer. That is, for various gravitational phase shifts. Okay. And then the ones on the right are a series of interferograms for various tilt angles for various magnetic fields. Okay, so we can do both of these, and we have to. That's the way this whole map of these interferograms we must take in order to have the operating point for the experiment. We must do that. We must just set the operating point for the spin-independent phase and the spin-dependent phase. Okay, so this is what that kind of data you must get. Okay, so here, final result. I'm doing all right for time, right? I have about another 15 minutes, right? Yeah. Okay. I mean, I can barely see this launch, so I can see that up there. Sorry. That's okay. Okay, go by there. So here's the final result. Now here's a table of the data. The final result here is the delta phi AC is 2.11 plus or minus 0.34 milliradians. That's the experiment. That should be compared with 1.51. So it's about this error bars there are the statistical standard deviations, 1 sigma standard deviation. So we're 2 sigma away from what you predict from theory, and there may be some other physics in that. We don't know. But, you know, let's face it, you know, sometimes experiments are 2 sigma away from what you expect, right? And sometimes the theory is not good, but I think theory is okay here. So the 1.51. So this is that's the experiment, okay? And the references to the experiment. Now, I don't expect you to come to any understanding of all of this data very quickly, but I would like to just make a few comments about it. You know, you can sort of look at the data and see kind of what the quality of the data is. But I do want to make a few comments about it. This experiment extended over 2 years. The data taking was divided into 2 segments, 1 and 2. That's you can see that in that table. And that has to do with taking data for the first year before the beryllium reflector of the reactor was changed out, and then everything had to be removed, and then all put back in, and the next year. That's what 1 and 2 means there. Data was further divided into 3 parts for the various operating points and the various slopes of the interferograms. And the total number of neutrons that were counted in the whole experiment over the whole time was of order 100 million. And less than 10% of all the data in the experiment was discarded due to reactor scrams, electrical outages, or electronic malfunctions. Okay, so that's it. It's the first time that the Aharonov-Kasher phase shift was directly observed. Maybe the only time yet. So I'd like to know if there is another experiment that you guys that are experts in other fields believe is a successful Aharonov-Kasher effect experiment. Now, of course, this effect comes up in many other applications in solid-state physics. But as far as a direct observation of the Aharonov-Kasher effect, let me know, because I'm not yet aware of it. I've made some mistakes in the past by saying that this has never been done or cannot be done or so, and I don't want to get into that. I should know the literature as well as you do. Okay, now what I'd like to do is I'd like to talk about the scalar Aharonov-Bohm effect. Okay, here it is. Suppose that I have an electron beam, and I divide it coherently into 2 parts. Part of the wave goes on path 1 through a bias potential, and another part goes on path 2 through a pulse potential, right? These regions are envisioned as small metallic cylinders with a pinhole, say, at either end to let the electron come in and out. That is, they are Faraday cages. So inside the Faraday cage, the electron feels no force. So suppose I pulse the electric potential on in cylinder 2, that's the, what is that, the lower path there, while the electron wave packet is inside of that little cylinder, and then pulse the potential off before it leaves. So there's no gradient in the potential. It's inside this Faraday cage. It doesn't feel any force. There's no wave by time of flight. You could tell that was turned on. But nevertheless, there's a phase shift, which is given by that the integral of the potential 1 over h bar e u2 over the pulse length. Okay, that's the idea. So this effect has never been observed without a hitch. Now, some people may come up with say, well, you know, that's no matter what you mean by hitch, because it's been attempted in many ways, and there is data from various places in various experiments. So I wish some Hasselbach and other people were here to tell me more about, you know, what kind of statement I should actually issue with regard to the success of the scalar AB effect or the electric AB effect. However, this effect has been observed with neutrons. And I show you it here at the bottom, in the bottom half of the slide. The original idea for this experiment was provided by Anton Zeilinger in 1985, and then by Anand in 1987, and finally we did the experiments in the late 1990s. Okay. So the idea here is that we have neutrons going through interferometer, and when neutron is in, say, that in the middle of that pulse coil on the bottom, we are in that pulse coil at the bottom. We turn the field up, then turn it up, down, turn it off before it leaves. So it's a long solenoid, so the potential mu b just comes up while neutron's in there. No force, because there's no gradient of the field, magnetic field. No force on the neutron. But there's a phase shift, mu b2, okay? Integrated over the pulse time. That's the scalar AB effect but with neutrons. In our case, it's we pulse the field on for 8 microseconds, turn it off for 64 microseconds, reverse it, and then turn it back on. So 128 microsecond cycle, and we repeat that many times and do detect neutrons time of flight. And you can tell by time of flight when the neutron was in the coil, inside, because we know when we detected it, and we extrapolate back when the neutron was in. So here's a typical, here's the geometry of the actual experiment. Okay, it's done in a skew symmetric interferometer. So you have those coils, the bias coil, just like in this with the electric effect, and a pulse coil. And we do it a slightly different interferometer shape. It's this one, okay? It's called skew symmetric interferometer, and you can come up and put this in your hand too, okay? Some people like to put one in one hand and one in the other. I don't know why that is. Some balance involved in there, I guess. Okay, so that's how the actual experiment was done in skew symmetric interferometer. It's a collaboration between us and the Melbourne group. So we do time of flight. Here's a typical time of flight spectrum here. You see, so it's a function of microseconds. And you see, again, it's called N2, and so these are C3, C2, sometimes called O beam, H beam, whatever. So the time of flight. So what we're interested in is the counting rate at the plateau regions of those time of flight spectra. That is, see if I can get this guy to work here, the plateau regions here or here. So we're really interested in the difference counts between there and up here, for example. Okay? That's what we're really interested in. And then plot that versus the magnitude of the pulse magnetic field. In this case, the pulse magnetic field was plus or minus 19 Gauss. So we want to plot that. Those counts as a function of the amplitude, the height of the pulse magnetic field, and that's what this is shown here. Okay, so here, let's look at this as unpolarized neutrons. So this experiment was again originally done with unpolarized neutrons, and with the same idea that I used in the AC effect experiment. You know, doing a polarization effect experiment, but with unpolarized neutrons. So here's the data plotted versus magnetic field. This is for, I guess, the C2 field on, field off, right, and then the other one. So they add up, and that fits the AB formula to within 1%. If you fit it with an adjustable pulse length, and the pulse length, we look on a oscilloscope, it looks like 8 microseconds. But if you let that as the adjustable parameter, it comes out to be 7.18 microseconds, and it fits it like a glove. So this is the scalar AB effect. Well, that experiment, because it's done with unpolarized neutrons, somehow caused what I call quantum confusion amongst some theorists. Again, okay, and there were a number of papers written, and they said it didn't really measure what we said it was measuring, and so on. They said it really should be done with polarized neutrons, and I said, yeah, no, polarized neutrons is really how much harder. But we took up that challenge 5 years later when Brendan Ullman from Australia was my postdoc, and we did it with polarized neutrons, with actually longitudinally polarized neutrons. That is, neutrons polarized along the direction of the motion of the neutron, which is along the axis of the solenoids, and they're a much, much harder experiment. There it is. And a young man was an undergraduate in my quantum mechanics class, Alexei Motrinich. He participated in this experiment, and Hal Lee was my thesis student, and they always regarded this experiment as their experiment, and still to this day they do. It was almost 10 years ago, beautiful experiment in terms of neutron optics and all that. And Alexei was just terrific, and now he's a He's a professor at Caltech. He learned how, he didn't know anything about experimental physics, but he taught me a lot, a lot about magnetic fields. And so these guys were just great. And, so we did this experiment with polarized neutrons, and data looks the same. I mean, it's not as high quality data as that, but the effect is the same. Okay, so that's the AB effect experiment. And this experiment is force-free phase shift, okay? Force-free phase shift like AB. It's torque-free. Neutrons, right? There's two states, Remember Basel, only up or only down, right? Only up or only down. It's a non-local interferometric effect. It is dispersion-free, okay? And it's non-dissipative. This experiment is AB in spirit and in fact. Don't ever let anybody tell you it's not. Okay? Did I get that, Herb?
I would tell you it's not.
See, he's one of these guys. Mike, you have some work to do on Herb.
The key to the Aharonov-Bohm effect is that there are two real fields that have real effects, the electric field and the B field. And the Aharonov-Bohm effect occurs where a particle that does interact with those fields has neither of them present.
Okay, see, this is a matter of your conceptual difficulties. Let's see, we have a few minutes, right? Okay, we have 3 minutes. So here's a photograph.
I have a different name for this.
You will. So here is the beautiful setup that we have at NIST, the Neutron Interferometry setup in the guide hall, 20 megawatt reactor. You're welcome to come and see it. It's a fancy vibration isolation system and so on, and we do kind of fancy experiments with it naturally. When I say we, I stopped doing hands-on experiments 3 or 4 years ago, and the guy that runs the group, this fundamental physics group, is Mohammed Arif. He's one of my students. He's my boss too. So he says if I want to get paid, I have to work. So. So that's our beautiful setup at NIST. Come and see us, okay? Call me. I'll show you where my... so if you want to learn more about this whole thing, this whole field, Ralph showed you this picture of this book yesterday. Here's the real thing, okay? And he and I it's 10 years old now, and he and I are anticipating with some trepidation and some difficulties writing a new edition of the book. And that's what we're up to right now. So it's 40 experiments, 1,200 references, 400 pages, costs us $100. Fantastic investment. Okay, so here's quiz. I promised, okay? Okay. I promised. And now, I don't know if you can read from that distance, but Herb, I give you a job. These are. Okay. So if you can't read from that, there is we pass out. Okay. Okay, and I will read it to you so that there's no question on what the problems are. Okay, so quiz actually consists of 2 quiz problems, quiz 1 and quiz 2. Okay, so quiz 1, that's the one on the left. Suppose I have an unpolarized, nominally monoenergetic cold neutron beam of velocity v, say, of 1,000 meters per second. The beam is chopped by Fermi chopper to produce a pulse as shown schematically. This pulse is directed along the center line of magnet gap of spatial dimensions d by L by W, where W is very large. That's perpendicular to the plane of the slide. Assume the magnetic field B is essentially confined to the gap region. That is, it is more or less uniform and static, and that the returned field is carried away by some appropriate magnetic yoke. Under what conditions, if any, will 2 pulses be observed downline as shown in the diagram?
Now, okay. At this point, I've got to interrupt with Sam. We could either take the quiz.
You don't have to take it. No. I give you the quiz.
You're not going to take it.
And it shows you my coordinates at the bottom. Okay. both by electronic mail, by mail, or whatever way, or by, you know, telephone. That's all there. Okay, so quiz number 2. It's this now. The first quiz was a warm-up for quiz number 2. Okay, so if you don't fare well on quiz number 1, hopeless. Quiz number 2, okay? Quiz number 2. Suppose that I have an unpolarized, nominally monoenergetic cold neutron beam of velocity v, about 1,000 meters per second. The beam is chopped by Fermi chopper to produce the pulse shown schematically. This pulse beam is directed along the center line of the gap between two electrically charged plates, very much like an AC effect experiment, okay? Of spatial dimensions d by L by W, where W is very large. Assume that the electric field E is essentially confined to the gap region of space and that it is more or less uniform and static. Assume further that there is no magnetic field anywhere. Under what conditions, if any, will two pulses be observed downline for each pulse of the chopper? That's quiz number 2. Okay? So, I know your names. I have a list of people here. So you can respond, okay, and send your answer to me. That, you know, may cause some difficulty for you historically later on. Or if you don't respond, since I have all your names, then I can say later on also historically, they didn't, you know, Mark Silverman thought it was just too damn hard. He didn't answer this question. Okay, so I leave it with you with that, and there's a lot to be learned here. And I should say up front that my neutron friends and colleagues have not done well on this quiz. Okay, so you can substitute atom beam people can substitute spin 1/2 atom for a neutron if you like, and that would work just fine. Okay, so.
You claim you know the answer, right, to your question?
I know the answer. Well, I claim I know the answer, but like a lot of other people too, I always leave that 2% in the back of my mind that I could be wrong. Okay, you must do that. Right, but I'm at that sort of that level of confidence. Okay.
But I think at this point we should thank our
Experiment
speaker. As the Aharonov-Bohm effect was elicited over the past enormous amounts of controversy, there must be questions. So please ask Sam your questions. Challenge him.
Yes, sir.
I have an experimental question. Back to your final results for the AC phase shifting.
Yes.
Those air bars look really funny to me. Were they air bars?
Uh-oh. Let's see. Previous. Let's see. What's going on here?
Just use the back arrow on your keyboard.
Oh, that's great. That's a great slide there. Oh, I should have shown that one. There's a quiz. Sorry. Okay. You were asking about the data table?
That one, yeah.
Yes. Okay.
But,
Yes,
I mean,
yes,
the
sir.
final results of those phase shifts really have very low scatter, but the air bars you put on them are really large. Was there?
Oh, these are difference counts. Okay. So there are difference counts between two very large numbers. Okay, because you see the difference counts have to do with switching electric field on and off, and that only changes the counting rate by a part in 1,000. Okay, is that okay? So when I take the difference of two very large numbers with great air bars, then you get these. Is that okay?
He repeated the experiment and it was too close to the same thing.
Yeah.
Just stick with the question.
Your error bar, Sam, would be plus or minus 1 standard deviation, or plus minus.
That's 1 standard deviation, right?
But it looks like if I just looked at the final results,
Yeah.
it looks like it'd be closer to 1/10 of a milliradian instead of 7/10.
Okay, okay. I don't know. They have to do the weighted average properly because you have to use all. This doesn't show all the data, by the way. You know, because you have both difference counts in the C2 detector and C3 detector. C2 detector, you know, there's some average background that's higher. So you have to take all that into account. Once you take that all into account for on all these different conditions, positive slope, negative slope, and all that, then it comes out to be that number. I mean, I would like to be smaller too, but
error bar should be larger than smallest value in your table.
isn't it?
No,
Not necessarily. Why is that?
Why no?
because usually you make many measurements with a reasonable error, And then you can average all the results, and that reduces your error, usually by a factor of
How many
square
times?
root by n.
Square root of n.
So
Yes,
that must be more or less.
Now, n is number of the
of the-
data.
of the-
Yes, right.
And the number of times you repeated the
So
measurements.
it's half of that. I
Now,
would
yes, yes.
estimate on that.
So these you see are sums of these on, off, high voltage on, off, and null, right? Over 30-minute cycles and taken over whatever it was, 9,000 some hundred, 209 times, okay? Okay, that's,
I'm going to actually ask that we not have additional questions. I want to try to keep to the schedule as we have it, although
Sure.
we always talk with Sam in the break that we'll have. Speaker next is Herman. Do you want to- and